Okay, today we want to talk about the derivative of exponential functions. I am just following exactly the book, but the lesson is actually quite long, so it will not be finished in 1 or 2 sessions. So you need to be patient a little bit. So I am presenting it exactly in a way that it is in the book, and of course it is a little bit convoluted if you want to see the whole picture. I'm just presenting it in a way that if you are interested, learn where this stuff is coming from. Okay, but the good news is that at the end you don't need to be very good in understanding all those hard concepts. You can just use the formulas to differentiate new functions. Okay, so that type of functions that we are dealing are called exponential functions. So if you remember, so far we had some formulas in our table of derivatives. Yes, so if you remember, we have a function here, and then we have f prime here. So if I have a constant, then the derivative is 0. If I have x to power, I wrote it c, let me write it a in this case. A is a constant, and the derivative is a times x a to power minus 1. These are the formulas that we have learned so far, and we solved a lot of problems using this simple formula, okay? And we have also some rules. If that I have the sum of two functions added, and I want to take the derivative, it becomes the derivative of the first one plus the derivative of the second one, which can be extended to more than two functions. And then we have the same scenario for the difference of two functions. It is f prime minus g prime. And if I have a constant, multiply the function, and I want to differentiate that, I don't care about this multiplicative constant. I just differentiate the function and then multiply the constant in. So these are the rules that we have so far. Yes, do you remember? So here it was very important to realize that x is your variable, a is a constant. Yes, a is a constant. Okay, so those type of functions that we had, for example, if I color me right with black now, if those functions, for example, if I write f of x equals to x to power a, these are called power functions. Okay, but if I interchange these two, a function that I get is called an exponential function. Okay, if I ask you, do you know the derivative of a power function? The answer is yes. That is the one in the table. Okay, today we want to learn, but we will not finalize it today. We will start talking about the derivative of these functions, but we will finalize it on Friday. Okay, it's a very long lesson. So I am asking you, what is the derivative of this function? What is the difference between these? How do you understand the difference between these two just by looking at the rule of those functions? The power function is a function whose base is variable x, its exponent is a constant. The exponential function is the other way around. Its base is a constant, its exponent is the variable x. So that is how you distinguish between these two. For example, if I want to give you an example of this function, you can say x to the 2. If I want to ask you to give an example of this function, you can say 2 to the x. Okay, so these are the differences. This is one type of exponential function, 2 to the x. This is one type of power function, x to the 2. But for example, if I choose a to be a negative number, then I will have trouble because sometimes this function is not defined at all. For example, assume that I take a to be negative 1. So can I talk about this function with leave, So the answer is no. For example, if I ask you calculate f of 2, you can calculate it. It is minus 1 to power 2. It becomes 1. But if I ask you to calculate f of 1 over 2, then what will happen? It becomes minus 1 to power 1 over 2. But what is the answer to this? Yes.
Square root of -1.
Which is undefined in the set of real numbers, yes? So it becomes square root of -1. If we are working in the set of real numbers that we do, are actually, we are doing everything in the set of real numbers, it is undefined. Yes? So because these kind of things does not happen and does not bother us, we want to make sure that this will not happen. So when we talk about this exponential function, we assume that this base is a positive number. Okay, so this is included in the definition of the exponential function itself. So when I say that I have a function, exponential function, what you need to think about is that you have a number which is positive, and then to the x. This is called an exponential function. Okay, an exponential function is a function of this form: a number, a positive number to power x. Do you think, for example, this is an exponential function, 2 to power minus x? Is this an exponential function? Why? Because this is not exactly x. Yes, I'm saying that it should be exactly x to call it exponential. Yes, why this? I can write it in this form. Because another name for 2 to power minus x is 1 divided by 2 to power positive x. But do you agree that I can write it in that way? 1 over 2 to power x. So if I ask you what is the base in this exponential function, you would say this is a. So if I ask you what is the base of this exponential function, if you say the base is 2, that's not completely correct. The base is 1 over 2, yes? Because when I write it in this form, it becomes positive x. I have to have a positive x here. So then this is also a type of an exponential function. Is that clear? Okay. But first of all, I want to make sure that you understand that asking the derivative of this is quite different from asking the derivative of this. I want you to feel that, okay? So, of course, if I ask you what is the derivative of this, you immediately answer 2x because of that rule. But remember, if I ask you what is the derivative of this, if you want to write, if you say x goes down and I subtract 1 unit from that, this turns out to be completely wrong. Okay, so this is not the derivative of exponential functions. But I want you to feel why do you at least expect that this is not the right formula. If you remember, we can come back and talk about the definition of the derivative, yes? Yes, do you remember what is the formula of the derivative? Someone else? Don't you care about this? Yes?
F of a plus h minus f of a.
No, the limit. Don't forget. The limit of what?
F of a plus h.
Not a. In this case, we have x. So f of x plus h, yes? Minus
f of x.
X, yes? Divided by h goes to 0, yes? So that was the definition of the derivative. Let me just review something here for you. If I want to use this definition for this function, let us see what happens, yes? So the derivative of that function for x squared, so f prime of x is the limit of what? F of x plus h means that I replace x with x plus h everywhere. So this becomes x plus h to the power of 2. And then I have x to the power of 2 because minus f of x divided by h goes to 0, yes? But let me write the same formula for this function. Let us see what happens. Yes. So if I write the same formula for this function, so this was the function f of x equals to x squared, and this is the function f of x equals to 2 to power x. Yes. So then what happens? This becomes the limit. Okay. Now, can you tell me what should I write? I am writing this definition for this function now. Of course, there is an h, yes, be optimistic. What you can write, you can just write here h goes to 0, there is a negative sign, okay? And then what is on the right-hand side of the negative sign for this function? Everyone, yes?
2 to power x.
2 to power x. And then what should I write on the left-hand side?
2 to power x plus h.
Agree? It becomes 2 to power x plus h because I'm supposed to replace s. And then at least you see that there is a very big difference between the algebra here and the algebra here. Yes? So if I ask you, how can you calculate this? you know what to do. It's very simple. You use the quadratic rule, you raise it to power 2, and then simplify it, and then you get the limits. Okay? But if I ask you the same question here, at least I want you to feel that the algebra is different from this. There is nothing to expand here. You understand? So here I have a binomial. I expanded to power 2. I used some rules to simplify that. But here I cannot use any rule to expand it. I am not telling you that I am solving this problem, but I want you to feel the difference. Why, if I interchange the role of these two, the problem suddenly becomes quite different. Is that clear? So because the calculation of this is a very elementary one, you need to find another way to calculate this limit, because this limit cannot be calculated exactly in this way. Is that clear? Okay. And by the way, it turns out that you don't know how to calculate this limit. You need to wait for university to calculate this limit. Okay. So this is not a simple one, but I want to follow exactly what is written in the book to motivate you how we can calculate this. Because the whole problem is to calculate this limit, agree? I want to calculate the derivative of this function. The derivative of this function is defined to be this. The only thing that I can do is to find a way to calculate this limit. When I am done, that limit is the derivative of this function. But at least you feel that there is a big difference between calculating this limit and this limit. Is that clear? Okay. Now, here, this was one example of a type of function, but let us not just work with 2, let us work with 8 for all the numbers. Okay, so let me clean this mess and then I start again. So is there any questions so far? Okay, yeah, this we don't need anymore. Now we start the lesson formally, okay? This lesson is actually very important, okay? With attention to it. Okay, so what I want to write in this list is the derivative. I intentionally put an empty space here because we cannot tackle the problem directly. So I want to put a formula here. So if I have a to power x, a is a positive constant. My goal is to answer this question mark. Okay, so let us start. F of x is equal to a to power x. Then the question is that f of x is what? F prime of x is what? We want to answer this question. We start the question today, but we finalize it on Friday. Okay. So here, let us start. Okay. What is the starting point? Again, help me to write that. I have a function. So don't get confused. X is your variable. X can change from number to number, but a is a fixed constant number at this point. I fix it and I keep it the same all over the problem. Okay, can you tell me what should I do for answering the question mark? What is the natural starting point? I have a new function. I want to find its derivative. So the natural starting point is just the definition of derivative. We don't have anything else in our. So I start with the definition. So let me just repeat this. F of x plus h minus f of x divided by h goes to 0. Okay? And then you know how to write this, yes? So I have the limit h goes to 0. The denominator is h minus sign. F of x is just my function, a to power x. And f of x plus h is a to power x plus h. Yes? At least we can do some algebra. Yes, let me make it clear. For this limit, which one of these letters, which one of these parameters is a variable? If I ask you what is the variable here, you definitely tell me x is a variable and a is a constant, okay? But now look here, I have a, one letter, x, 2, h, 3. So I have 3 letters here, and I am calculating a limit. I'm asking the same question. For this limit, which one of these parameters that you see is a variable? Yes?
X.
Yes?
H.
H. In this case, H. Why? Because the limit H goes to 0. It means that I am not allowed to change X and A. I am calculating this limit for a fixed A from the beginning, but for a fixed X here. But what I am doing, I am changing H by making H smaller and smaller. I'm sending H to 0. So none of these parameters is changing except for H. Is that clear? I am sending H to 0 here. Okay, so this is important to understand. And then the next step is to use a very nice rule of exponents. Yes, how can I decompose this into the product?
A to the power of X
Times A to power H, yes? And then I have minus A to power X divided by H, H goes to 0. And then you can simply see that I can factor this factor out, so it becomes A to the X. What is left from here when this is pulled out? A to the H is left and minus 1 is left. Yeah, please let me know if there is something that you don't understand. Is that clear? Yes, so I pulled this factor out. This was a common factor. I pulled it out. Why this is correct? If you don't believe, you can multiply it back in your head. Multiply this by this, it will produce this one. Multiply this by that, it will produce this one. So what I have done is completely correct. Is that clear? But now, as I told you, is this changing for this limit? As far as this limit is concerned, can I say that this is some constant number? Yes, because the variable is H. I am not touching this A, I'm not touching this X. So A to the X is something that I am not touching at all, but I am affecting this by changing H. I am making H smaller, so this will change, so the whole expression will change, and I am sending H to 0, so I am changing this H, the denominator also changes. So this part is variable, but this part is constant. When I have a constant, I can pull it out from my limit. So this becomes A to the X multiplied by this limit, A to the H minus 1 divided by H, H goes to 0. Yes? So the whole problem is how to calculate this limit, because if I calculate this limit and it becomes a number, any number, I have that number, I multiply it by A to the X, and that would be my answer, because I'm looking for that. So the whole point is that I don't know how to calculate this. Okay, so but I know something. I can clean this question mark, and I put this here and keep it for future. So this becomes A to power X multiplied by the limit of A to power H minus 1 divided by H. H goes to 0. So is that understandable? So I haven't succeeded fully in finding the derivative, but I realized that I found a very nice relation. I found the derivative of this function is more or less itself, except with a multiplicative constant. And this is a very nice property, because, for example, if I ask you what is the derivative of x to the 3, then the answer is 3x squared. This is not a constant multiplied by the same function. You see, the functionality is changed. X to the 3 has reduced to x to the 2. So this is no longer the same function. But the property here is very nice. If I have this function, its derivative is the same function without any changes, multiplied by a number. Okay, so that's a very nice property of this function. But of course, it depends on your definition of being nice. Okay. Okay, so is that clear? So the only thing that we concentrate now is to have some idea of, try to calculate this limit. If I can calculate this limit, then I am done. And I told you that if you want to calculate this limit rigorously, it is beyond the scope of this lesson. So, but I will follow what is written in the book, and I have to use my notes. Okay. The book is following this. This is a good method, actually, to motivate you. The book says that, okay, let us take A to be 2 for the time being. Okay, let us concentrate on this particular value for A. Not because of my goal is to calculate this for all positive values of a, but let us say what will happen if I choose a equal to 2. Okay, so it means that I am interested in the limit. Instead of a you put 2, it becomes 2 to power h minus 1 divided by h goes to 0. Okay, so this is there any way to calculate this? There is a way, but for the time being, you need to follow your instincts somehow, yes? So I'm just following the numbers in the book, okay? And then, so for example, you have this table, h. When I am sending h equal to 0, in principle, if I want to calculate this limit, I have to do it rigorously. Do you remember? Sometimes we factorize, we cancel something, but this is not possible here. So there is no other way for you at this level unless to just understand the concept of limit. So it means that I calculate this function for h equal to 0.1. It's a small number, but not very small. Let us see what is the formula. So then I will write 2 to the power of h minus 1 divided by h here. Okay, so I have to use the calculator. So you put this number inside in here instead of h, and you calculate using your calculator. What you get is this number. Okay, nothing is very clear now. I go to the next number. If I want to make it smaller, another small number is 0.01. Yes, but if you calculate this, you will get this number. Okay, and then if you make it even smaller, I'm saying this is not the proper way of calculating the limit. This gives me an idea. Okay, but this is the only way that you can do it. So you see, I calculate this one, it becomes this number. And then I even make it smaller, it becomes this number. Yes, something like this. And first of all, you see that there is no nice pattern to guess. Which number is that? Yes, it's not easy to guess because you will see that this is not a number that you can immediately guess the limit. Okay, so this is why really it is important to calculate the limit rigorously, not just following this, because there is not a very good pattern to see. Okay, none of these guesses are the exact value. Okay, but you can see that at least 3 digits are stable now. If I go, for example, at least you can see 2 digits are stable. So I can say that this limit is approximately 0.69 or something. But if I ask you what is the exact limit, you don't know, and I don't know right now. Okay, is that clear? But we can say that that question mark is roughly this number. But my point is that it is smaller than 1. Okay. Now let me change the number. Instead of having a equal to 2, let me change the number and have it. Let me clean these things. We don't need them. So let me change a to 3 this time. Okay, and then focus on this function, on this limit. So let me write this function here. And I will do the same thing as I did for this limit. So I put 0.1 here, then I will get this number. And I put the other one here, I will get this number. And then I will get this number. And finally, I will get this number. Again, it is not clear what that number is, but at least you can rely on these 3 digits, for example, 1.09 or something. Okay, so this is approximately 1.09 something, but the point is that this number is greater than 1. Okay, so let me just review what I have done. My point is to calculate this limit for all positive real numbers a. I don't know how to calculate this, but I changed the way that I am looking at the problem. I will change a with 2 and set up a table for small values of h, and I see that the numbers for this function are these numbers, at least it gives me a feeling that this limit should be around this 0.69, okay? But the important point is that this number is smaller than 1, okay? Now I change a to 3 and I do the same thing for the new function. I will get these numbers. It doesn't give me exact value, but it gives me the feeling that this limit is somehow greater than 1. Is that clear? Something like that, not more than that. But this will motivate you somehow. Might be, there is a number so that the limit for that particular number is exactly 1. Because if I choose 2, the limit becomes smaller than 1. And if I increase from 2 to 3, suddenly the limit becomes bigger than 1. So it might motivate that, might be there is something between 2 and 3, so that if I calculate the limit for that particular number, the limit becomes exactly equal to 1. I don't know, is that okay or not? So I am calculating this limit for 2. It becomes a number which is definitely smaller than 1. And then I calculate the same limit for another number 3. Next, after 2, 3, I see that the limit is something bigger than 1. Okay, so the limit for 2 is smaller than 1. The limit for 3 is bigger than 1. So it might happen that there is a number between 2 and 3, so that if I calculate the limit for that particular number, it turns out that the limit is exactly equal to 1. Okay, this is just a motivation. The proof that this number really exists is not very hard, but it's a hard subject. It's beyond the scope of high school mathematics. That number is called the Euler number, and it's a very, very important number. Okay, so let me keep this one. So what we learned that the limit of 2 to power h minus 1 divided by h goes to 0 is smaller than 1 by this table. And then the limit of 3 to the h minus 1 divided by h goes to 0 is greater than 1. This motivates us to conclude there exists a number, a positive real number such that this a positive real number between 2 and 3 such that this limit for is exactly 1. This limit for that number exactly 1 is exactly 1. Okay? So it turns out to be true. This turns out to be true. And that number is called the Euler number. The Euler is the Swiss genius mathematician, actually. So is called the Euler number, and it is denoted by E for Euler. Okay, so this is the introduction of this Euler number. So if somebody asks you what is the Euler number, now can you tell me what's the answer? What is the Euler number? Yes?
Between 2 and 3.
Oh, that is the approximation. But what it is? What is the property of the Euler number? The property of the Euler number is the number which makes this limit equal to 1. Okay, so this is the definition of the Euler number in your book. Okay, so what we are saying is that what Dylan said is the approximate value for E. Yes. So do you agree that E should be between 2 and 3? Yes, because for 3 the limit was bigger than 1. For 2 the limit was lower than 1. So yes, what you said is right. The value of E is between 2 and 3. That is correct. This is the value. I don't know the value exactly, but I know that E should be somewhere between 2 and 3. Yes. And if I ask you what does this mean, you should say this is the only number for which this limit is exactly equal to 1. So this means that the limit of E, that mysterious number that we don't know it yet, but we say that there should be a number so that this limit is equal to 1, and then we call that number the Euler number. So this is very important to remember. Okay. Is that clear? So that is the definition of the Euler number. But of course, you might want to have a better approximation for E. Okay. So how we can find a better approximation? Of course, that is a rough approximation that this number is somewhere between 2 and 3. But if I want to find a better approximation, assume that you have your calculator with you, and then you want to use this formula to find a better approximation for E. What do you do? What do you think we can do? For example, you have your calculator, and now you know this formula in front of your eyes. You want to use the idea of a limit and this exact formula to find a better approximation for E. For example, right now, if I ask you, do you think E is below 2.5 or bigger than 2.5? You cannot answer, yes? What you know is that E is somewhere between 2 and 3. But is it closer to 3 or is it closer to 2? It's not clear yet. But can you use your calculator to have a better approximation for this? You don't need to do it. Just tell me what to do. I will do it here for you. So assume that you have your calculator. You want to find a better approximation for this number. Yes?
You can put 2.5 as the variable, or yeah.
Yes, and then
calculate the approximate limit, like you did with the table before.
I think the logic should be the other, because if 2.5 it gives you a number. How do you know that this is closer to that real number or not? You see,
that's true.
Yeah. I mean, the logic should be a little bit different. Anyone else? Okay, what you can do, you can understand what is the limit. Just tell me if you understand. From this one is equal to 1 when h goes to 0, I can conclude that e to power h minus 1 divided by h is approximately equal to 1 under one condition. What that condition is? Because what is the meaning of limit? When you say the limit of a function is a number, it means that the value of the function becomes close to the value of the limit under one condition. If you respect this, if you respect that h is small, then the value of this function becomes close to the value of the limit. That is the meaning of the limit. Do you remember when I say the limit of f of x, x goes to a, is equal to L? What does this mean? Do you remember? This means that when I make x close enough to a, the values of the function get close to L. Is that clear? That was the meaning of the function limit. So when you say that the limit of this function is equal to 1, it means that this value is close to 1. When you say this value is close to 1, what does it mean? It means that this is approximately equal to 1. Under one condition, under the condition that h is very small. So I would write this for the small values of h. Understandable or not? Yes? So is this conclusion clear for everyone? I cannot just ignore this part. I cannot say that this is approximately equal to 1. You can test it. There is an E button on your calculator. If you want, you can test it. If I take h to be 100, then this is extremely bigger than this one. It is not close to 1 at all. This becomes close to 1 if I follow this rule that h is going to 0. So if h is small, then this is approximately true. Okay, then let me multiply both sides by h. What happens? It becomes e to power h minus 1 is approximately equal to h. Yes, if I multiply that. But again, let me not repeat it. For small values of h, this is correct. Let me move 1 to the right. So this becomes e to the h is approximately equal to 1 plus h, again for small values of h. Now I want to find e. Can you tell me what should I do? I want to have e alone here on the left-hand side. I have an exponent here. I want to get rid of this h because I want to find an approximate value for e. How should I get rid of this h? Yes?
H root.
H root, yes, but h root is not a good word because this, when you say nth root, n should be an integer. There is no guarantee that this, but what you say means e to power h to power 1 over h. Yes, this is different from saying eighth root, yes, because when you say nth root, n should be an integer, a natural number. Another way, so what you mean is this one, yes? Okay, so this becomes approximately equal to 1 plus h to the power of 1 over h for small values of h. If you don't understand something, please let me know. By the way, this is h, not n. Is that clear? I am saying that this is approximately equal to this. Then I raise both sides to this power. Yes, why I raise this to this power? Because now this power with this exponent will be multiplied by this exponent and it will give me 1. And e to the 1 is exactly e. And this is approximately equal to 1 plus h to the power of 1 over h for small values of h. Is that clear? Yes or no?
Yeah.
Now, let me write this back in the form of a limit. Can you just help me to do that? You see, I had a limit. I wrote it in approximate value form for small values of h. Now I have an approximation for small values of h. I want to turn it around and write it as a limit. So how can I write that? Just say something. Yeah.
Does it become 1 plus h minus 1?
No. I'm saying that write this as a limit. You see, I had a limit which has this equality, exact equality. I took this limit. The price that I have to pay is to change this to approximate value. Okay? So when you say the limit of this function is exactly 1, it means that the values of this function are approximately equal to 1 if h is equal to 0. And I did some algebraic calculations with this approximation. Then I want to turn this approximation into exact equality again. So how should I write it? Just say something. I know that you know it, but you don't dare to say it. I want to say e is equal to limit. Can you help me? H goes to where at least?
0.
0, because this is a small values of h. H goes to 0. Okay, which function? You see it on the board. It's 1 plus h to the power of 1 over h. Yes, this is the same function. Is that clear? Is this something mysterious going on? I know this lesson is a little bit hard, but this is real mathematics, by the way. So far, it was just a game. Yeah, so you need to learn these things, okay? So is that, by the way, all of them are in the book, so I'm not telling you, you probably know me for some person who just talk more than the book, but this is exactly in the book, okay? So is that clear now? So here, I wanted to calculate this limit. I couldn't.
So I chose for 2, for 3. I motivated that there should be a number between 2 and 3 with that property. Then before continuing to my main goal, which was calculating this limit for all numbers, I'm just pausing for a while to discover a little bit more about this number. Then I will continue to my main goal. Okay? So you might say that, for example, if I ask you what is pi, the famous pi number, you know that pi is between 3 and 4, but you know better. You know pi is 3.14 something at least. So this is what I want to do for E again. For the time being, I know that E is between 2 and 3. I want to know a little bit better about E. Is that clear? Now I told you that if this is going to be true, this means that this is approximately equal to 1. If this is approximately equal to 1, I multiply both sides by h and I will get this. Is that clear for everyone? And then I move 1 to the right-hand side, I get this one. I raise both sides to this power. Why? Because this power and that power will be multiplied together, and then you will get e to power 1, which is I want to. Then I will get this. Of course, you can keep it in this way. You can say e is approximately equal to 1 plus h to the power of 1 over h for small values of h. You can stop there, but I want to write equality because we care about equality more than approximate values. So if I translate that sentence, do you believe in this one now? This tells you that this function is approximately equal to e if h is a small. This means that if I calculate the limit of this function when h goes to 0, this becomes e. Is that clear? Yes or no?
Yeah.
Okay, so these are the formulas. I don't remember that are they given in the formula sheet or not, but these are extremely important. Okay, so this is another way of looking at the function e. Now I give you your calculator and then tell me how to do it. I have my numbers here. So you have the formula for E and you want to find a better approximation for E. You have your calculator. Tell me what you do. Yeah, I have to refer to these numbers. I don't have them in my mind. Okay. So tell me, what do you do to understand that, to have a better approximation for E using this formula? Yes?
You need to switch out h for 0.
Send h, no, switch, if you cannot switch h for 0. That is the problem. And that is the power of limit. You see, can I switch h to 0? You mean send h to 0.
Yeah.
Okay, so switch h to 0, it means that you replace h with 0. That's the problem. So that is the power of looking at limits instead of values of the function. Because if I ask you, what is the value of this for h equal to 0? Can you put h equal to 0 to this and get the answer? No. Because unfortunately 1 over 0 is not defined. But you can make h very small, and that is the idea that we do. So I will set up a table. I will have h here. I will have 1 plus h to power 1 over h here. And then I will start doing the same thing. I make h small. For example, 0.1, 0.01, 0.001. And then this gives me better and better approximations. Of the approximation are this. So if you put this number 0.1 in your function, use your calculator, the answer that you get is 2.5937. This is the answer that you get. It's good to check these things with your calculator. But if you put this number there, you will get this 2.7048. So far, how many digits are there that I can rely on? Can I rely on this first decimal point? No, it's not stable yet. You see, it is changing. But I am sure about 2. But this is not a big deal because I already know that E is between 2 and 3. So that is not a good information. So it means that 0.01 is not good enough for me for the time being. So it motivates me to go to another stage. So if I do this, it becomes 2.7169. And now how many digits I can rely on? 2. So I know that this is approximately 2.7. Yes, so it is bigger than 2.5. But if I do this one, which is done in the book, so this one gives you 2.7181. Okay, Now, how many digits I can rely on so far? 2.71. Okay, let us check for the other one that is written in the book, I think, if I have done it correct, if I remember. So it becomes 2.7183. So how many digits I can rely on based on this calculation? Yes? 2, 7, 1, and 8. They are stable. So this means that E is approximately equal to 2.718 up to 3 decimal points. Yes? To 3 decimal points. Agree? But usually people, I have it in my memory by 2 decimal points. So it is 2.72 if I round it to 2 decimal points. So it becomes to 2 decimal points. Yeah, is that understandable? So we now have a rough approximation of this famous and ubiquitous constant number in all mathematics. So pi and e are the most famous constants in mathematics, okay? So we know roughly now that this is 2.72 up to 2 decimal points. But might be you ask me what is the exact value of e. The bad news is that there is no exact value of e, because in higher mathematics, it can be shown that e is irrational. It is not easy to prove that. You see, because the proof that we have here is very artificial. So it was very hard to see why this number, which was a little bit mysterious, came into our calculations. And this number, we cannot finalize the decimal points because it turns out, it is proven by mathematicians that e is an irrational number. When it is an irrational number, it means that the decimal points will never end. It's exactly like pi. Even if you go 2,000 digits after decimal point in pi, it is not finalized, yes? And there are some people can memorize, by the way, those number of digits, yes? Is that clear? So that was a little bit of deviation. My goal is to answer this limit. I haven't succeeded yet, but in my journey or expedition to reach to this answer, what did I do? I suddenly introduced a constant number and then pause a little bit. That's a little bit of digression, so that I want to talk a little bit about this constant number e. What we discovered is a very, very nice formula for limits. Okay, so this, if I ask you to calculate this limit, you need to have it in your memory. This calculation of this limit is not like the calculation of this limit. When I ask you to calculate this limit, you don't need to have something in your memory. You just factorize it and cancel it out. Yes, so you can immediately do that. Yes, but here there is nothing to cancel out. So this is why sometimes calculating limits are not straightforward at all. So you need to be very creative and smart thinking to be able to find the limit. This is one of those limits. If you want to just use these rudimentary methods for this limit, this does not work at all. Okay? So this is one famous formula in whole mathematics. The limit of 1 plus h, 1 to the 1 over h when h goes to 0 is equal to. Okay. And now e is approximately equal to this number, and we know that e is irrational number. Okay, can you tell me now, this is a very nice property. Yes? So can you tell me what is the derivative? Let me state it in a slightly precise way. So you see that my goal was to do what? Do you remember? My goal was to calculate the derivative of this function. For which values of a? For all positive values of a. For example, 2 to power x, I want to know the derivative. 3 to power x, I want to know the derivative. I don't know, square root of 2 to power x, I want to know the derivative. So these are my questions. Yes? But one of these numbers could, in principle, be e to the power of x. And I want to answer this right now. What's the answer? What?
e to the power of x.
Why?
Because the number to the left is the natural log.
No, forget about natural log. Natural log comes later. Yes?
The limit of e
Uh-huh.
is 1.
Yeah, by definition. So if I ask you this, go back to this formula. Replace A with E. What happens? Instead of A, put E. Then tell me, what is f prime of x? According to this that I saved for future reference, I told you. Everywhere that you see here, change A with E. Yes, what will happen? F of x is equal to e to the x implies that f prime of x is equal to what? Is equal to e to power x multiplied by the limit of e to power h minus 1 divided by h goes to 0. Agreed? This was the formula which was correct for all positive values of a, including this positive value. Yes? But now, can you tell me what is this number at least for this particular number? Yes? That was 1. So this is 1. Do you remember? That was the definition of e. And if I multiply 1 by that, it becomes the same function. Is that understandable? Let me repeat it again. This formula was completely generic. It works for all positive values of a, regardless of the value, particular value. If you put a positive value for a, this formula is always true. We proved that. That was exact proof. Okay? But now, let me change this number a to number e. Can I do that? Yes, because we know that e is also a positive number. So I replace a with e everywhere. Yes? Then this will be the result of the calculation. But for this e, this is easy to say. What is the answer to this? Was 1. Do you remember? And then if I multiply it, it becomes e to power x. So it's a very nice property. If I have this very specific function, nothing will happen if you differentiate it. Yes, it's a very nice property. This is the only function in the whole universe with that property. So the derivative of the function is equal to itself. Nothing changes at all. Is that clear? So this we know. So it means that I couldn't answer this question mark, but I found something interesting. If this a is e, then the answer is the function itself. Is that clear? So I was not able to answer this question mark yet, but I was able to answer something which is also interesting. And this is the only function. I haven't shown that this is the only function. I showed you that this function enjoys this property, but there might be another function with this property whose derivative is equal to itself. But it turns out if you know a little bit of differential equations, you realize that this is not the case. This is the only function with this property whose derivative is exactly equal to itself. Nothing will change. Is that clear? It's a very, very important property. So you see, still my question mark is here, but I was able to find a formula not for every a, for this particular a. Any questions? Yes or no? Okay. So before continuing, let me give you some examples. This example is important for the exam. So everything that I covered here was in the book, but at the end of the day, you should be able to calculate the derivatives of different functions involving these kind of functions. Yes? So let us do some practice. This problem that I am doing right now is important, is the type of problems that you will get in exam. Okay? So let us do some practice. Okay, so example. Differentiate. Okay, so number 1, for example, I have f of x equals to 1 over 2. So let me write it in this way. yeah, e to power x divided by 5 minus 2 e to power x plus 1. So for example, you want to differentiate this function. How do you do that? Let me, this is not a very nice example because nobody writes like this. Let me write x to the 3 plus 1. I want to differentiate this function. This is something that you need to know. And the good news is that I want you, if you are interested in mathematics, this is kind of advanced mathematics. This is the way that people do mathematics to discover new things. But the good news is that you can totally forget about what I said so far, and then try to differentiate this function using that formula. Okay? So the formula that I have is added to this table today is this formula. We still don't know this. Okay? So I want to differentiate this function. So can you tell me how should I do that? Let me review everything. So here I want to differentiate this function. Do you think that this is really a fraction? Because if it is a real fraction, we don't know how to do it. You need to wait until math 4, yes? But this is not a real fraction because I can write it as 1 over 5, exactly, e to power x. Yes? And then minus x to the 3 plus 1. This is the first thing that you need to think of. And then, sorry, this is not f. This is f itself. And now I differentiate. If I want to differentiate, this is the difference and the sum of 3 functions. I need to differentiate the first one. Okay, so let me just do it. You don't need to write this in the exam. You can do it in your head, and it's better. Minus the derivative of the second part plus the derivative of the third part. You don't need to write this. You don't need to write that. It is better to do it in your head. Okay, but you need to understand what is going on. Okay, now can you tell me what will happen with this constant? One of these rules is important here. Which one? Which one? The third one. Because it tells you that if you have a constant number multiplied by function, don't care about the constant at all. You just write 1 over 5 and differentiate your function. The derivative of this is easy. We had it before. The derivative of 1 is 0. But this is the new lesson. What is the derivative of e to power x? This is the kindest probably function ever. When you deal with derivatives, nothing will change, yes? It becomes 1 over 5 e to power x itself, and then I have minus 3x squared. Is that understandable? Yes? Okay, let me give you one more example that is important for the exam as well. So, example. Let me add one to it and then one more example. Number 2, what do you think about this? G of x is equal to e to power x divided by 2 plus 2 divided by e to power minus x. I want to differentiate this function. Okay, can you help me to do that? What should I do? Yeah?
So the first one, you take 1/2 times e to the power x.
So that is clear. Yes, thank you. So it becomes 1 over 2 e to the x. But what about this one?
Then you take 2, I wrote it as 2 divided by 1, divided by 1 over e to the power of x. Then you flip.
Yes.
So you get 2 times e to the power of x divided by 1.
Yeah, you don't need to write so many, but you're right. You can just do it quickly. So I have 2, I have e to the power of minus x, I take it up, and it becomes positive. That's right, completely. So this becomes 2 e to power x. Is that understandable for everyone? That the exponent was negative. When I bring it up, it becomes positive. But what Dylan said is actually the detailed way of thinking about this. What Dylan is saying is that you write this as 2 over 1 multiplied by 1 over minus 1x in your head. But 2 over 1 is just simply 2. And then this is the definition of negative powers. Do you remember, if I have something to a negative power, I can bring it up and make it positive, yes? Times e to power x. But 2 times this can be written compactly as this one. If you really want to understand what's going on, this is the way that you need to think, but you don't need to write it if you can do it quickly in your head. Okay, but of course I can simplify it a little bit more, yes? Because I have 1/2 of this plus 2 of the same thing. So what happens then? It becomes 5 over 2 e to power x. Do you agree? I have 2 boxes. I have half of a box added to it. So it means that I have 2.5 boxes. That's the same story. Yes? And then I want to take the derivative. This is so simple. What is the derivative, by the way?
The same.
The same. Yeah. So I realized that I think I made a mistake when I said that is the only function whose derivative is equal to itself. This any function multiplied by a constant. Yes. So if you have e to power x, the derivative is equal to itself, but it doesn't matter if you multiply it by any constant, the derivative of that function is also itself. So this is the derivative. Understandable? Okay. Just one more example here. So this, if you understood what is going on for the exam, you are on the safe side. But if you want to understand mathematics, you really need to understand all of those stuff that I told you. So again, let me repeat. Don't let these, if this is complicated, don't let this scare you, because what you need in the exam is just these simple calculations. Yes? Is that clear? Okay, another example. It's also a famous one. It's a prototype example. I told you, remember this. And that is about the tangent line. Yes? Now I have a new function, so I can talk about tangent line to the graph of that new function. So for example, I would say determine. This is also another example which is important for the exam. So determine an equation for the tangent line determine an equation for the tangent line to the graph of the function f of x equals to, say, for example, 5e to power x at the point on the graph whose x coordinate is 0. So these two examples are the only examples that you need to do very well for the exam based on what we learned today. The hard part of this was deriving the formula. But if you are that kind of person that you don't care about why this is true, you don't need to know why this is true, you can just use it. Okay? Okay, so now how should I solve this problem? This you need to know. The steps are always the same. Finding an equation for the tangent line is a very important example, and it is always the same. The only thing that differs from problem to problem is the function and this number. But if you know the algorithm, you just follow the same rules over and over again. So can you tell me what should I do? I need to find a slope. Yes, when you say the tangent line, you know that the form of the tangent line is of this form. Do you remember? Now, I have two questions to answer, 2 question marks here. What is k? What is m? What is k is related to the derivative of your function. So what you need to do for k value, you need to differentiate your function and calculate the derivative at this x coordinate of the point of tangency. So k value is f prime of 0. This is the only thing that you need to remember from derivative here. Okay, but I told you if you want to calculate f prime at a number, the priority is not by replacement 0. The priority is to differentiate first, and then when you found the derivative, replace it with 0. Be careful about it. You are not allowed to put 0 first. You have to calculate the function, the derivative. The derivative is today's lesson. What is the derivative of this function? F of x is equal to 5e to power x. This is a little bit confusing, so let me write all the steps because the derivative is itself. But this is a very nice coincidence. So why the derivative is itself? Because 5 goes out, and then I need to take the derivative of the function, but the derivative of this function is in my table, so it becomes 5e to power x. That is a coincidence. So let me just repeat that. That was not the only function in the universe. That function multiplied by constant is all those functions. It's a group of functions. Okay, but now tell me, what is k value? K value is f prime of 0. After the differentiation is finished at this point, I need to replace the x with this number. So it becomes 5e to power 0. But what is the answer to e to power 0? E is a number. We learned that this is around 2.7. So what is e to power 0?
1.
1. And then it becomes 5 times 1, which is 5. So the k value is 5. How should I find the m value? I would write y is equal to k value is 5. M value is missing. Do you remember how should I find the m value? I need to find the point of tangency. The x coordinate of the point of tangency is given directly in the problem. It is 0. But can you tell me how should I find the y coordinate of the point of tangency? How should I calculate? Have you forgotten? These are the things that you need to know. You need to replace 0 in the function. Yes, don't get confused, because here the function and its derivative are exactly the same. You might get confused. But for k value, you have to put the number in the derivative. For y value of the point of tangency, you have to put this value in the function. Yes? So the y value becomes what? F of 0, and which is coincidentally equal to 5 itself. So this is a coincidence. The k value is 5. The m value, the y value of the point of tangency is also equal to 5. So instead of y, you replace it with 5. Instead of x, you put 0, and then you get m. What is m? This is totally gone, and then m becomes 5. And then when everything is finished, you write your answer. Your answer is y equals to 5x plus 5. This is your answer. So these two examples, I told you that these are the only things that you need to be worried about to know very well in the exam. How to differentiate functions, how to calculate tangent lines if an exponential function of this form is involved. And if you want to have a deeper understanding where this formula is coming from, you need to understand what I said here on the board. Okay, I want to do something else and then we finalize, which is not a very good thing, but this is done in the book. I have to do it. So the book tells you that what happens if I put a constant here, because this is so boring, yes? If I just give you e to power x, I think that is actually a very bad way of doing it, but this is done in the book, so let me do it. So they say that, okay, if you have e to power x is equal to e to power x, what happens if I have a constant here? Yes, and a constant here. Let me see what would be the derivative of this one. But let me test your understanding first. Can you answer the derivative of this function for me? Let me see. How do you answer this question? If I don't multiply x by a constant, just add a constant to it. I give you f of x equals to e to power x plus 5. What is the derivative of this function? That is different. I haven't given you the formula here. So forget about this. What you have here is this. Using this formula, can I answer this or I need one more rule? Do you think we can solve it? This is not exactly that, so I'm not allowed to use exactly that formula. But you can use that formula with your previous math knowledge to be able to differentiate this one. That's what I'm saying. But how? Yes?
E to the power of x times e to the power of 5.
Yes, okay, so that's the first step, right? So if you don't mind, let me write e to the power of 5 times e to power x. Do you think I can differentiate now? The first step is correct. If I ask you what is this one? E is a constant. It's a strange number, but who cares? It's a constant. 5 is also a constant. So e to power 5 is?
It's 0. The derivative is 0.
No, the derivative of this is 0, not the derivative of the whole one. Which one of these rules is important? Now the third rule. Yes? Because how do you this is the only way that you need to learn. If I ask you what is the derivative of this one, yes, you are right. The derivative of this one is 0 because that's a constant. Yes? But this is the whole function is not a constant. It is a constant multiplied by a function. It's a constant multiplied by a function. I want to differentiate it. So what is the derivative? Can you tell me what should I write? So yes, e to power 5. I don't care about the constant. You see, I differentiate the function. Is that clear? But now, is this in our table? Yes. The derivative of e to power x is e to power x itself. So it becomes e to power 5, e to power x. Yes? And then if I can combine it back. Yes? So the derivative of this function, but that's also in the same category because that's a constant multiplied by the function. So the derivative of this one is itself. So if you get a constant added to x in the exam, that's not a big deal. You don't need a new formula. Is that understandable? But if I right now ask you, what is the derivative of this? Let me write 5 again. If I add 5 to it, you need to learn this. This is also an exam problem, okay? If I add 5 to it, any constant to x, you can still do that derivation, this differentiation. But now if I ask him what is the derivative of this, that's a new story. Yes? I didn't want to talk about this, unfortunately. This is not according to my taste, but we have to do it because it is in the book. Okay, so I want to add that formula there because this formula is a particular case of an advanced formula called the chain rule. But if you learn it here, I have this experience. When you go to Math 4, you don't appreciate that this is the same rule. You think that this is a rule, chain rule is a different rule, but they are the same rule. But anyway, might be the authors think that, okay, this is so boring, let us make it a little bit more fun by putting a constant there, okay? So this I want to answer now, if I have time, which I don't. I want to stop because I don't want. But the question is that I want next time I will start with this formula. What happens if this is not so boring? I have a constant c here, okay? Then it turns out to be the same function again, but a constant goes down, okay? So this is not finished yet, not finished. Yes, we will finalize this next session. And then hopefully we can cover everything. And then this will give rise to a very important concept of natural logarithm. Okay, so then you need to